In this video, we are going to be covering parsecs, arcseconds, and astronomical units. If these terms sound alien to you right now, don't worry. By the end of this video, they're going to be like water. First, let's start with some pictures. So there are a few basic ways to measure distances for objects in space. And let's look at these two pictures. One way we can measure an object in space is by observing a point right here. Let me choose a different color. Observing a point right here, and then later observing a point right here. And we're going to see the object in two different places in the sky. From point A, we're going to be seeing the object here, because we're going to look this way. And at point B, we're going to be seeing the object over here, because we're looking this way. And from this, we will get a shift in the object. And with that, we can do some trigonometry to calculate how far the object is away from us. Similarly, we can do that by going around the sun instead of just going around the earth. Similarly, we can do that by going around the sun instead of just going around the earth. At one day of the year, we can start observing from here, and then 6 months later, we can take another observation from here, giving us similar pictures. One object is on this side of the sky, another is on this side of the sky, and there's going to be a little shift in between them. Again, using the same trigonometry, we can calculate the distance between us and the object, because we know the distance from the Earth to the sun. We know the angle of separation. From that, we can find the distance. Now, before we move on, let's just remember the distance between the Earth to the sun is 1 astronomical unit, which is defined as 1.496 times 10 to the power 11 meters. This is something useful to keep in mind when we're going to be defining parsecs and arcseconds in a bit. Now let's move on. Let's draw a triangle similar to the one up here. So we'll have an object over here. We'll have our Earth over here. We'll have our sun over here, and we'll finish the triangle. So when this distance is 1 astronomical unit, and this angle is 1 arcsecond, and 1 arcsecond means if you take 1 degrees and you split it up into 60, you get 1 arc minute. And then if you take that and split it up into 60 again, you'll get 1 arc second. So that's where this arc second is coming from. We use arc seconds in astrophysics because angles in space can get really small, and it's easier to define them with the We use arc seconds very commonly in astrophysics because angles can get very small, and it's not very We use arcseconds in astrophysics very commonly because angles can get very small, and it doesn't always make sense to use a bunch of decimal places with degrees. So you'll see this showing up a lot. Just remember, this is degrees, this is arc minutes and arc seconds. And they come from dividing by 60 and dividing by 60 again. So when this happens, when this is 1 astronomical unit and this is 1 arc second, we define that, this long side, as 1 parsec. This parsec just happens to be equal to 3.26 light years. And that's equal to 3.086 times 10 to the power 16 meters. Now, before we move on, I'm pretty sure you can tell, since we have an angle and 2 sides, we're going to be using a lot of trig in these types of problems. So let's go over what a small angle approximation is. It's basically saying that sine theta is equal to tan theta is equal to theta. Now, before we move on, I'm pretty sure you can tell that we're going to be using a lot of trigonometry because we have an angle and 2 sides. So let's go over what a small angle approximation is. It's saying that when we have sine theta, we can set that approximately equal to tan theta, which is approximately equal to theta. So whenever we're using sine theta or tan theta in a problem, we can easily replace it with the angle itself, and we'll get about the same answer. From this, we can get a formula that says d equals 1 over p, where d is the distance from the object in parsecs, 1 stands for 1 astronomical unit, and p is the angle in terms of radians. Having this p, which is the parallax angle, in radians is pretty weird, but we have to be mindful to always convert from arcseconds to radians whenever needed. But it's because radians are used whenever there's some ratio in our answers, and having radians doesn't mess with our units at the end, like degrees would. We don't want degrees in our units hanging around at the end of our answer, right? So in these types of situations, we should always use radians instead of degrees, even though we have our arcseconds, which is a form of degrees. This formula might be a little bit confusing with all the unit conversions, so let's go over some example problems. So first, let's start with how many astronomical units are in a parsec? Okay, so let's try to remember our triangle that we drew. We had 1 AU over here. We had this angle to be 1 arcsecond, and over here we had 1 parsec. We're trying to find this in terms of AU. So let's start by writing our formula. We have D equals 1 over P. Here we have 1 parsec and 1 arcsecond. So let's plug that into our formula. We have 1 PC and 1 arcsecond. But remember, whenever we're using this formula, we have to turn this into radians. So let's start by doing that. Let's get this 2 degrees first. So this is arc minutes. Now this is degrees. Now let's turn this to radians. Putting this into our calculator, we can get 4.8448 times 10 to the power negative 6, and this is radians. Now let's put this back into our formula. We'll have D, which is 1 parsec, equals 1 over the answer we just got. So that would be 206,265 astronomical units. Because at the top we had this was 1 AU, and with radians, we don't keep radians in our final answer, but we do have to keep degrees. That's why we converted, so we don't have degrees in our distance answer. And we get 1 parsec is 206,265 astronomical units, and that's our final answer. Let's move on to the next problem. If a star's parallax is 0.1 arcseconds, how far away is it? Instead of jumping right to the formula, let's think about this for a second. We know that D, which is the distance between the object, is inversely proportional to the parallax angle because we have 1 over P, right? So if the parallax angle is, what we had before was, this is 1 arcsecond, and then this is 1 parsec. So if we divide this by 10, this would need to be multiplied by 10, right? Because it's inversely proportional. So intuitively, it makes sense to say that D should be 10 parsecs. And that's correct, but let's see why. Let's start by converting 0.1 arcseconds into radians. Again, we have arcseconds to arc minutes, then arc minutes to degrees, then degrees to radians. Now with our calculator, we get an answer of 4.848 times 10 to the power negative 7. Notice how this is exactly 10 times less than the answer we got before when we converted 1 arcsecond into radians. Now we have 0.1 arcseconds, so our answer makes sense. Again, this is radians. Now let's put this back into our formula. So D, which is in parsecs, 1 astronomical unit over the P that we got. And with our calculator, we get that D should be 206,265 astronomical units, which is exactly 10 times the answer we got before, giving us 10 parsecs. And that's our answer. Let's review one more time. First, we went over 2 ways that we can measure distances in space. Then we tried doing that ourselves by defining a triangle that has 1 astronomical unit on this side. We have 1 parsec on this side, and this angle is 1 arcsecond. When we're given problems, we can get angles of any size, we can get distances of any size, but that doesn't stop us from finding the missing side of the triangle with this formula, where the distance is in parsecs. Here, this 1 stands for 1 AU, and the P, the parallax angle, is in radians. And don't forget the small angle approximation. Whenever you have sine theta or tan theta in a problem, you can just substitute that with theta. That's only if the angle is really small. And lastly, we went over some example problems. I hope that helped. Thank you. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.